Today, I suggest we take a step back and look at our planet's atmosphere like you've never seen it before. Air, we spend our whole lives breathing it. We all live in it, and most of the time, we forget it even exists, because the gases it contains don't seem like much. They have no smell, no color. Transparent, they usually don't sting your throat or stick to your skin. So much so that air movements, when they're not carrying some dust, can only be seen thanks to fair weather or storm clouds swirling around without knowing any borders. But for the past few years, all that has changed. Because thanks to data collected by satellites and ground sensors, we are able to translate these chemical compositions into colors and thus see with our own eyes the elements constantly swirling in the moving air. Even when it is transparent, we can track these components drifting in the air and contemplate the breadth of the earth, see its size, its fits of anger, observe plants as they inhale and exhale, cities and factories spewing smoke, filaments from forest fires, and even dust from the deserts, being lifted and carried, sometimes all the way to the other side of the world. That being said, let's begin our journey by focusing on the movement of microscopic particles suspended in the air. What you're observing is the distribution all around the globe of what are called aerosols. Tiny particles that are lifted from the ground or the surface of the oceans by the winds, then carried away by air currents. On this animation, which brings together 6 weeks of observation data, you can see in purple the dust lifted by gusts of wind sweeping across the world's great deserts. And they can carry the particles lifted from the ground thousands of kilometers away from their region of origin. In orange and red, you can see what is called black carbon. That is, the particles emitted by forest fires, whose smoke carried by the winds can travel across a large part of the planet. By observing black carbon, we can see the progression of fires raging in North America, the Amazon, and Siberia, as well as the amount of firewood burned for heating and cooking in Africa every time night falls. Above the surface of the oceans, in cyan and white, are marine salt particles, suspended in the air by the movement of the winds, which clearly show the paths of storms and cyclones. Finally, the green plumes, which spread all around the planet, show the sulfate particles. Produced by coal or oil-fired power plants, heavy industries, as well as volcanic activity. In this other animation, centered on the North Atlantic and with different colors, the representation of sulfate particles has been left out. To focus only on forest fires, sea salt suspended in the air, and dust particles lifted from the surface of the Sahara, which we can clearly see here being carried by storm systems, and crossing seas and oceans to be deposited in Europe and even in the Gulf of Mexico. Hurricanes and tropical storms stand out against the dark blue background of the ocean, carrying large amounts of sea salt particles in their swirling winds. And you can see that as the storms intensify, they can pick up dust from the desert in their winds before washing it out of the atmosphere through rain. The white clouds you can see forming correspond to the smoke produced by the massive wildfires raging in the northwest of North America at the time when the measurements for this animation were taken. In just a few days, the microscopic ash particles contained in these plumes can travel thousands of kilometers, even being carried by powerful high-altitude atmospheric currents across the Atlantic all the way to Europe. In this other video, we focus only on fine particles with a diameter of less than 2.5 micrometers. These aerosols, which are at least 28 times smaller than a human hair, are suspended in the air by winds sweeping across large desert regions, but also by diesel engines, coal power plants, cooking and heating wood, and even forest fires. The higher the concentration in the air of these microscopic particles, which can lodge in the alveoli of the lungs, the more dangerous it is to breathe the air in the affected region. The kind of wave that seems to sweep across the image at regular intervals is due to the fact that we are watching entire days of emissions pass by here. And when night falls, the winds do the same. And while the activity in large urban centers decreases, a small portion of the particles lifted from the ground will settle back there. Thus, as small as they are, fine particles generally remain in the atmosphere for only a few days to weeks because they inevitably end up falling back down under their own weight. It must be said that these particles are real giants compared to the molecules swirling in the air, which we are now going to focus on. These impressive images show the major regions emitting sulfur dioxide. 90% of the sulfur dioxide present in the atmosphere is due to human activities. Sulfur dioxide is released in very large quantities by the combustion of coal, fuel oil, and gasoline. In this animation, you can easily see the large urban centers and other industrial regions that burn large amounts of fossil fuels, as well as the nearly 10% of emissions that have a natural origin and for the most part come from volcanic activity. Look there. You can clearly see the volcanic plumes rich in sulfur dioxide released by a major eruption that occurred in New Guinea. You can also see the ongoing activity at the time the measurements were taken. From Piton de la Fournaise in Réunion, as well as Mount Etna in Italy, but also some volcanoes on the Kamchatka Peninsula and in the volcanic arc of the Aleutian Islands. I'll give you a few seconds to have fun finding other active volcanoes on your own. Those are the effects of the Nyamuragira eruption in the DRC in 2006. Even though volcanoes are, in the long run, minor players compared to the steady, massive scale of our emissions, it does occasionally happen that a volcano releases as much sulfur dioxide in a few days as the industry of an entire country does in a year. In 1991, the eruption of Mount Pinatubo in the Philippines alone was responsible for nearly a third of the annual sulfur dioxide emissions. And the spread of these molecules into the stratosphere caused the average global temperature to drop by 0.5 degrees for 1 to 2 years. Okay, now I'm going to show you another absolutely mind-blowing animation, because by looking at the concentrations of nitrogen oxide in the air near the surface, you can literally see the major global shipping routes. Because the distribution of nitrogen oxides, which only last a few hours in the atmosphere, roughly matches the major urban and industrial regions, but also the network of main maritime trade routes, along which cruise ships and other container ships emit large amounts of this element, which can damage the respiratory tract. In this other animation, you are watching, over the course of 2 consecutive weeks, the changes in ozone concentrations near the surface. But don't go associating the soothing blue of this animation with good news, because ozone can be an angel or a demon, depending on the altitude where it is found. In the stratosphere, between 15 and 35 kilometers in altitude, it acts as a UV filter that protects living beings on the surface from the powerful solar rays that break DNA or cause cells to mutate. And without its presence, the Earth would probably be sterile, at least on the surface. But lower in the stratosphere, that is where we live, breathe, and complain in traffic jams, the ozone produced is not a shield, it's a poison. A byproduct of modernity. A toxic pollutant for plants and animals. The wave you see moving in the image comes from the fact that surface ozone concentrations vary considerably between day and night. Because some of the ozone produced during the day by the action of sunlight on nitrogen oxides and volatile organic compounds is destroyed at night before reforming the next day. You are now looking at the regions responsible for the emissions of terrifying carbon monoxide. This molecule, which at high concentrations can disrupt the blood's ability to carry oxygen and cause fatigue, headaches, dizziness, and confusion, is the result of incomplete combustion. The highest concentrations point to large megacities, industrial infrastructures, but also regions where people heat and cook with wood, as well as forest and peat fires, as you can see here in Indonesia. There too, you can see the times of day progressing, especially in Africa or India, when people put the pot on the fire. Unlike nitrogen oxides and ozone, which have a short lifespan, carbon monoxide can persist for nearly 2 months in the atmosphere, which means it is transported by air currents over very long distances. All the elements we've talked about so far are pollutants, unlike the 2 big ones I've saved for the end, which pose no danger to health. At the concentrations they are found in the atmosphere, but which, paradoxically, over the long term, pose threats of a completely different level. These two chemical elements are the main greenhouse gases found in the air, carbon dioxide and methane. You are seeing the dispersion of methane around the globe from these emission regions. This powerful greenhouse gas stays in the atmosphere for less time than carbon dioxide, but each molecule of methane has a warming power 84 times higher than that of CO2 over a period of 20 years. As a result, it contributes to about a third of current global warming. Here, the distinction between the different sources of methane in the world is not made. And emissions from infrastructures that extract or burn fossil fuels, those emitted by wetlands, flooded rice fields, or even open-air landfills, are observed without distinguishing between them. And to a lesser extent, forest fires, biomass combustion, permafrost thawing, and even termite activity, which host microorganisms that allow them to ingest wood and cellulose while generating methane as waste. So termites contribute to nearly 2% of the world's emissions of this gas each year. What you're seeing right now are the places in the world where methane emissions from decomposing organic matter are concentrated in regions with wet, waterlogged soil. Regions covered with ponds, lakes, swamps, or rice paddies, which together produce nearly a third of the methane released into the atmosphere each year. And you can see that the rhythm of emissions follows the seasons, shifting from north to south and vice versa as we enter winter or summer. In this other animation, we're focusing only on methane that originates from agricultural activity. So you're mainly observing large livestock farms, or in other words, the farts and burps of mammals, as well as the emissions produced by the fermentation of roots in rice paddies. Combined, flooded rice paddies account for nearly 10% of global emissions, while the flatulence that accompanies the digestion of ruminants such as cows, goats, and sheep alone accounts for nearly 20%. And now here are the methane plumes. They are directly associated with human activity, oil field operations, coal mines, and gas pipeline leaks, which combined are responsible for nearly a third of the total volume of this gas that is released into the atmosphere each year. Here, you can see the plumes escaping from Chinese coal mines. Over there, those coming from oil fields in the Middle East and elsewhere, where flaring is practiced. A technique that involves burning, often incompletely, the gas present in oil deposits. This plume, located in Turkmenistan, originates from leaks in a large gas field, which contributes as much to worsening climate change as the total greenhouse gas emissions produced by a country like the United Kingdom in a year. As for these continuous emissions coming from eastern Borneo, they are almost entirely due to the drying out of peatlands. Normally, the swamp forests that grow on these waterlogged, organic-rich soils sequester carbon. But when these soils are deliberately drained and burned to be cleared, then turned into palm oil plantations, they release the methane that had been stored there for centuries. It is estimated that due to the peatland fires that occur there, this region emits as much methane into the atmosphere each year as Germany does. And now we come to the distribution of carbon dioxide emissions. The colorful images you are looking at show the cumulative emissions over an entire year of these molecules, which are responsible for nearly 3/4 of global warming. And they too know no borders, spreading quickly from the regions of the globe where they are emitted to the entire planet. Here, the more the colors in the animation shift toward red and purple, the higher the concentrations of CO2 in the atmosphere. You can see that the plumes of carbon dioxide spewed by the major emitting regions swirl and disperse according to the prevailing winds, before gradually dispersing into the atmosphere, where it will drift for centuries or even millennia. The gray plumes correspond to the carbon monoxide emitted by the giant forest fires that rage in the summer in both hemispheres. During the first months of the year, the atmosphere of the northern hemisphere is continuously loaded with carbon dioxide. But once summer arrives, the concentrations start to drop slightly and the red and purple colors begin to fade. This decrease is linked to the seasonal variations in the plant growth cycle, as plants absorb a significant amount of carbon dioxide during photosynthesis, which they use to make sugar, leaves, wood, or fruit. Because of this growth, in spring and summer, plants temporarily remove some of the gas released into the atmosphere by our activities. But when autumn and winter arrive, this growth slows down or even stops. And then plants release more CO2 than they absorb and the levels soar again. So that by the end of the year, only half of the carbon dioxide emitted by the burning of fossil fuels has been absorbed by natural land and ocean reservoirs. The rest has accumulated in the atmosphere. The pulsing of the southern and northern lungs is striking in this other model, created from data collected during the summer in the southern hemisphere. In Africa and South America, you can clearly see this phenomenon of plant respiration through large pulses centered on the vast forested regions, such as the African and Amazonian tropical forests. If these pulses follow the rhythms of day and night, it's because plants absorb carbon dioxide during the day when they perform photosynthesis using sunlight and release it at night. Alongside this natural respiration, we can still see the practice of slash-and-burn agriculture in many places around the globe, as well as large urban areas and industrial infrastructures that emit CO2 almost continuously. All these emissions take nearly 6 months to reach and envelop all regions of the globe, as this other animation starkly shows us. If the mixing between the north, where the majority of anthropogenic emissions come from, and the south takes so much time, it's because the warm air present at the equator acts as an obstacle, slowing down the mixing of air between the two hemispheres. But over time, the newly injected CO2 will inevitably end up being diluted throughout the entire planet. On this other model, you can see how the seasonal exchange flows evolve over time during the second half of the year between the atmosphere and the terrestrial biosphere. During autumn and winter in the northern hemisphere, trees and plants stop growing and the leaves they lose decompose, releasing a large part of the CO2 that was removed from the atmosphere in spring and summer. These natural emissions are added to the atmosphere along with those continuously released by humanity. As a result, CO2 levels reach a peak at the beginning of spring. Overall, these large seasonal waves with their slow and steady breathing exhale as much CO2 as they inhale. But human activities produce a large net excess, which accumulates in the atmosphere. Thus, at the end of each cycle, there are nearly 2.5 additional parts per million of CO2 in the air. And it's amazing to think that CO2, which today makes up 0.04% of the air, isn't even one of the 3 major components of the atmosphere, which is composed of 78% nitrogen, 21% oxygen, and 0.93% argon. Yet, even though it's present in only a very small amount in the atmosphere, the presence of these molecules has significant consequences. Since the beginning of the industrial era, when we started burning large amounts of coal and later oil and gas, which took the Earth millions of years to create, CO2 concentrations have risen from 280 parts per million to over 420 today. The last time our planet's atmosphere had this much CO2 was nearly 3 million years ago. Back then, the oceans were 20 meters higher. But the inertia of the system means that today's sea levels have not yet reached such heights. All these molecules and other particles in the air, you're currently breathing them in. Every day, an average of 11 cubic meters of air passes through the lungs of each human on this planet. And even if we don't feel them, the elements we find there and that we've seen swirling on a large scale have an origin and a history. Their concentration is a mirror that indirectly shows us what we burn, what we raise, and what we destroy. In the atmosphere, there is the memory of our exhaust pipes and our industrial choices. Today, the tools we have created to analyze what's in the winds give form and substance to what is usually invisible. By recording the slow and powerful beats of the biosphere and human societies, they show us the earth breathing. And the presence of these colorless gases, which are the voice and face of the climate, should remind us that we are all in the same boat. That every day we live in the same atmosphere, a gigantic hole that knows no borders and has seen its temperature rise globally by more than 1 to 1.5 degrees since the pre-industrial era. But this figure is a misleading average, a statistical mask which hides the extremes of the climate. It is already more than 3 degrees warmer on average at the North Pole and more than 5 degrees in some continental regions in the summer. And being both part of and witnesses to this feverish surge should encourage us to change course. Maybe looking at the Earth as a planet that breathes is already the first step toward wanting to protect it, to prevent it from eventually suffocating. This was a bit different from what I usually do, so I'd be curious to know what you think about this kind of format. In the meantime, well, I'm going back to writing an episode focused on winds and atmospheric rivers. I hope you'll like it.